Let's try to analyze a differential equation of type m of x comma y dx plus n of x comma y dy. Okay, let us suppose this is a differential equation that I have got. Okay, we are going to assume that there exists a function u of xy such that you have del u by del x equal to m of xy, and you have del u by del y equal to n of xy. Okay, we are just assuming that there is a function like this such that partial derivative of that function with respect to x is m of xy, which is this, and partial derivative of that function with respect to y is equal to n of xy, which is this. Okay, now as per my knowledge of partial derivatives, I know that du is going to be equal to what? Du is equal to del u by del x into dx plus del u by del y into dy. Right? Now what I would do is I would just replace delta u by, or rather del u by del x by m of x comma y and del u by del y by n of x comma y. So what I would get is, let us see, I'm gonna have du equal to m of x comma y dx plus n of x comma y dy. Okay, which is essentially my original equation. Okay, so if du is equal to this, then obviously what I would have is, look, this is given as 0, right? And I say that du is equal to this, which is equal to 0. Okay, so essentially you are saying derivative of u is equal to 0. Therefore what you have is u is a constant. Okay, therefore what you can say that u of xy is equal to a constant, and this u of xy is equal to a constant is called as a solution of this differential equation. Okay, it is called as an implicit solution. Okay, this is a implicit solution of differential equation given by this equation. Okay, we have just assumed that there exists a function like this such that its partial derivative with respect to x and y is these two. If this is the case, then that function equal to a constant is the solution of your differential equation, which is given by this. Okay, and we call this as an implicit solution because we are not getting a y as a function of x, rather what we have is f x comma y as a constant. Okay, we are not getting a explicit expression of y, rather we are getting a expression of x and y, which basically equates to a constant. So we could solve this implicit solution to arrive at an explicit solution. Okay, if you have x square plus y square is equal to c, then this is a implicit solution because what you have is f of xy equal to a constant. However, if you have y is equal to c minus x square upon whole square root, then this is your explicit solution. Okay, so this particular type of differential equation is called as an exact differential equation if such a function exists. Okay, what type of a function exists? A function that serves these two conditions, okay, that follows these two conditions exists, then we say that this type of a differential equation is a exact differential equation. Okay, and this particular differential equation's function is called as a potential function. Okay, so what is a definition of an exact differential equation? The definition of an exact differential equation is a differential equation is exact if there exists a potential function let's call it as u of xy such that del u by del x is equal to, let us see from here, m of xy, and del u by del y is equal to n of xy, where m of xy dx plus n of xy dy is your differential equation. Okay, let us try to solve this question on the basis of discussion that we just had. Okay, on the basis of the information of exact differential equations that we just had. So if I would like to compare this with a standard form of an exact differential equation, which is m dx plus n dy, then I would realize that my m of xy is this and my n of xy is this. Okay, let us just assume that there exists a potential function. Okay, so I am just going to write over here, assuming potential function exists, okay, and it is given by u of xy such that I have del u by del x equal to m of x comma y and del u by del y is equal to n of x comma y. Okay, now my problem is basically about finding this potential function. Once I found this potential function, then the solution of this differential equation is going to be u of x comma y is equal to a constant, alright, as we discussed earlier. So let us try to find this potential function. I have del u by del x equal to m of xy. Okay, so my u is going to be equal to what? It is going to be equal to integration del u by del x dx. Okay, wherein I would assume that y is a constant. Okay, look, you have a partial derivative. Okay, when you take partial derivatives with respect to x, you are going to assume that y is a constant. Therefore, when we are going to integrate this guy, we are going to assume that y is a constant in this expression. Okay, so my u, or rather u of x comma y, okay, let's write it as u of x comma y. U of x comma y is equal to del u by del x, which is equal to m of x comma y, which is equal to this guy. Okay, y into 1 plus x plus cos y. So I have y into 1 plus x plus cos y integration dx. Okay, I'm going to assume that y is a constant when I'm doing this integration. So I would get this is equal to y is a constant, integration of 1 is going to be x, so I have y into, there is no integration sign, I have y into x plus integration of 1 by x is going to be log x plus cos y is a constant, so integration of 1 is going to be a x, so I have plus cos y into x, and I am going to have a constant, okay, a constant of integration. But since I am saying that I am taking y as a constant, therefore I cannot write this simply as c, rather I would have to write it as a function of y, okay, where this function of y is your constant, okay, because your constant terms can have y's in them, therefore we cannot write it simply as c, rather we have to write our constant of integration as a function of y, okay, which is unknown to us. So I'm just going to write in over here that this is a constant of integration, okay. So we have reached to a point where we know our function u of x comma y partially, okay. If I could solve, or if I could get the value of f of y, then I know my function u of x comma y. Let us try to get what is del u by del y based on this equation that we have got. Del u by del y based on this equation is going to be what? It is going to be, you are going to differentiate with respect to y taking x as constant, right? So what you are going to get is, x is a constant, so you have a 1, or rather let's call it as yx plus y log x plus cos yx plus f of y, and we are doing del by del y of this, okay. Now let's solve. So this is going to be equal to x plus log x plus x into minus sin y plus differentiation of this guy. Differentiation of this guy, let us suppose it is equal to f dash y, okay. So what I get is my del u by del y is equal to this, okay. But I also know that my del u by del y is equal to n of x comma y, okay, which is equal to this, okay. So I would say that this expression is also equal to n of x comma y, okay, and it is equal to what? It is equal to x plus log x minus x sin y, okay. So this is equal to x plus log x minus x sin y, right? So what you get is, if you compare over here, you have a x, you have a x, you have a log x, and you have a minus x sin y, okay. Therefore what you are getting is your f dash y is a constant, right? Or your f dash y is 0, okay. So let us say that this is my equation number 1, okay. This is my equation number 2, okay. What is 2? 2 is this. Del of u by del y is equal to n of xy, which is equal to this. This is my equation number 2. If I compare 1 and 2, I would realize that f of, or rather f dash of y is equal to a constant or is 0, right? Therefore my f of y is a constant, right? If your dy by dx is equal to 0, then it implies that y is equal to a constant. Similarly, if your f dash y is 0, then it implies that f of y is a constant, right? Therefore, I have found out my expression for u of x comma y, right? My expression for u of x comma y is y into x plus log x plus cos y into x plus fy, which is a constant. Okay, so I'm just going to write over here that u of x comma y is equal to x, where is it? We are over here, is equal to y into x plus log x plus x into cos y. Y into x plus log x plus x into cos y plus f of y, which is a constant. Let us say it is equal to k. Okay, so I have u of xy equal to this. Therefore the solution of the above differential equation is u of x comma y is equal to a constant. Therefore my solution is y into x plus log x plus x cos y plus k is equal to a constant. Actually, if you take this k over here, then you would have c minus k, which in itself would be a new constant. Okay, so I am simply going to say that y into x plus log x plus x cos y is equal to c1 is the solution of my differential equation, which is given over here. Okay, just understand one thing. Your equation of the form mx comma y dx plus nx comma y dy is not always exact. Okay, for example, let us take equation which is like this: y dx plus dy is equal to 0. Over here what I have is mx comma y is equal to y, okay, and nx comma y is equal to 1. Okay, this is 1 into dy, right? This is y into dx, so my mx comma y is y and nx comma y is 1. Now if I say that there exists a potential function, then I would have u equal to, or rather I would have del u by del x equal to mx comma y, right? And I would have del u by del y equal to nx comma y, right? If a potential function u exists, then these are the conditions for that potential functions. So my u is going to be what? U is going to be integration mx comma y dx, where I am going to assume y as a constant, right? So this is going to be equal to, my mx comma y is a y, so this integration is going to be equal to x into y plus a function of y, okay, or let's call it as a f of y. Okay, this is my constant of integration. Since I am assuming y as a constant. When I get a constant of integration, it would have terms of y. It may or may not have terms of y. Therefore, I am going to write it as f of y. Right? So, my u is xy plus f of y. Therefore, my del u by del y is going to be what? It is going to be x plus f dash y. I also know my del u by del y is equal to n, which is equal to 1. Okay, so if this is your equation number 1 and this is your equation number 2, from 1 and 2 what you get is x plus f dash y is equal to 1, right? So what you have is x plus f dash y is equal to 1, which basically tells you that f dash y is equal to 1 minus x, right? And your fy is going to be what? Your fy is going to be integration of 1 minus x. This is what? F dash y, right? Which is essentially d by dy of fy, right? So your fy is going to be integration 1 minus x dy, okay? So your f of y is essentially equal to 1 minus x into y plus a constant of integration. Now you see that your f of y is essentially a function of x as well as y, okay? However, we said that f of y is essentially a constant which should be having either constant things or y's. It shouldn't have x, okay? Therefore, we can say that we cannot have a potential function for this particular equation, okay? Because when you try to find out f of y, what you are getting is f of x as well as y, okay? So I'm just going to write in over here, f of y is a function of x as well as y, right? Which negates our original assumption, right? Therefore, a potential function does not exist, okay? We had assumed that my constant of integration is f of y, which contain terms like k and y, okay? However, my f of y is coming out to be like this, which contains terms which have x's also. Therefore, a potential function for this does not exist. Therefore, this guy is not exact, okay? You cannot solve it by the method of analysis of a exact function, okay? So I'll just